In this lesson, we're going to talk about what an equation is, and we're going to explain exactly how they relate to algebra. Now, in order to form any kind of equation, I'm going to need to introduce you to a new kind of object, which we call a comparison operator. Now, comparison operators allow us to compare two different expressions, and upon comparing them, we can decide that the statement is either true or false. Now, the simplest comparison operator is equality. Now, the symbol we use for equality is this equal sign over here. As I said already, people tend to reuse this symbol to mean equivalence or equality. But what I'm saying when I'm talking about equality is I'm saying that the value on the left is exactly the same as the value on the right. And this is true when the two numbers line up perfectly on the number line. Now, just to demonstrate the idea here, this statement over here is obviously true, because 5 is the same thing as 7 minus 2. The values are the same, or they line up on the number line. But in the second case, 7 equals 6 is obviously a false statement, so you could replace all of this for the word false. So unlike equivalence, when we write equals, we aren't guaranteeing that the left side is exactly the same as the right side. It is possible for the statement to be true, and it is also possible for the statement to be false. The next comparison operator I want to talk to you about is called the inequality or not equal operator. It basically tells us that the left expression and the right expression cannot be the same. So you can basically put this purple dot anywhere you like and they will not be equal, as long as they're not directly on top of each other as I've drawn before. Again, just to make the point clear, I've shown two examples. We can say that 7 is not equal to 6 is a true statement because 7 is not the same as 6. However, 8 is the same thing as 6 plus 2, so the statement 8 is not equal to 6 plus 2 is actually a false statement. Now the next comparison operator to talk about is the less than operator, and it's basically going to be true anytime the left-hand side is actually to the left of the right-hand side on the number line. So to give examples of these, we can see that negative 3 is in fact smaller than negative 1. Or in other words, if you drew them on a number line, here's 0, here's minus 1, and here's negative 3. Because negative 3 is to the left of minus 1, this is true. On the other hand, however, we would say that 3 is actually bigger than 1. So 3 is less than 1 is definitely a false statement. Now the next operator to talk about is the greater than operator. And it's going to be true anytime the left is actually larger in size than the right-hand side. Or graphically, we'd expect this purple dot over here to appear to the right of this yellow dot. So again, just to give two examples here, we can say that 7 would actually show up to the right of 2. So this means that this expression over here is actually true. On the other hand, 9 is actually a smaller number than 19. So that means this second expression is false. It's also important to consider what would happen if the left-hand side is actually equal to the right-hand side. If we write 10 is greater than 10, this is actually a false statement because 10 is the same as 10, or in other words, it's equal to 10. So you cannot write that 10 is greater than 10 and expect it to be true. Now the last two operators I'm going to show you are formed by just joining up other operators. So for example, less than or equal to is just a less than sign with an equal sign joined to it. And it's going to be true anytime either 1 or 3 is true. We draw this graphically by drawing the exact same thing, but then going around the yellow part as you saw here. Now the last operator is the greater or equal operator. And it's going to be true anytime equal is true or greater than is true. We just denote it by drawing a greater than symbol and putting an equal sign on it. You can see that the picture is exactly the same as the greater than picture, but we just draw this. Now that we've actually talked about all the different types of comparison operators, we're finally ready to tell you what algebra actually is. So at least in the basic case, algebra is designed to actually solve problems that involve any comparison operator and a missing pronumeral. The whole idea of algebra is to actually find all the values of the pronumeral that make the whole expression true. So I've just given two examples here. Both of these problems are actually problems you'd solve while studying algebra. You can see that in both problems there's a missing pronumeral, which is this x. And in both of these problems we have a comparison operator. The top one has equals and the bottom has less than. Now as you work through these problems, you're going to find a whole bunch of techniques that you can use to find the values of x that make either of these expressions true. Now one totally fine way to actually try solving these problems is by trial and error. You can choose x to be basically any value you like and see if the expression is true. So for example, if I tried x equals to 2, well 2 squared is the same thing as 4. Then 4 times 7 is the same thing as 28. Now if this whole term here is 28, then 28 minus 3 is the same thing as 25. And you can clearly see that 25 is not the same thing as 4. So this expression is false when x equals 2. If however you tried x equals 1, you'd find that this expression is true there. For example, 1 squared is 1, 1 times 7 is 7, and then 7 minus 3 is 4. As you can see, 4 is equal to 4, so this is equal when x is equal to 1. Now, it turns out that it's possible to have more than one value that make either of these true. In fact, for this bottom one, there are technically an infinite number of values that make it true. So we'd like to find a systematic way of actually figuring out what values of x make these true and exactly how many of them there are going to be. Now it turns out that there are a bunch of different ways that this could go. So let's talk about all the different possibilities on a new page. Now let me go ahead and say this up front. Algebra is easiest when you're dealing with equality. All of the other comparison operators are a fair bit more complicated. If an expression contains an equality operator, we call that expression an equation. Now whenever you deal with equations, you basically just need to follow the golden rule. And as long as you follow it, if you started off with a true statement, then you will always have a true statement. So the golden rule is really easy to state. It basically says that anything you do to change the value of the left must also be done to the right-hand side as well. Now, it's very important that we talk about this idea of changing the value. For example, when you multiply the left by 1, you're not changing the value, so you don't really have to multiply the right by 1 as well. So I've just started here with a really simple expression. I think we can all agree that 7 is the exact same thing as 5 plus 2. So this is definitely a true statement right now. Okay, so suppose for a moment I decided that I wanted to subtract 3 from the left-hand side. If I did that, then the left-hand side would now be equal to the number 4. Okay, now when I do this, you can see that the left-hand side is the same as the number 4, but the right-hand side is the same as the number 7. And this is the reason why I didn't write the equal sign yet, because they're not equal. However, if I also subtract this 3 from the right-hand side as well, then they will actually be equal. So this is the whole idea of the golden rule here. If you start with an expression that's true, if you do the same operation to the left and to the right, you will still preserve the trueness of the expression. So you started with 7 equals 5 plus 2, but then by subtracting 3 from both sides, you now have 7 minus 3 is equal to 5 plus 2 or minus 3. And since this was equal, this is equal as well. But there's nothing special about subtracting 3. For example, let's try squaring both sides. Okay, so if we square the left, we get 7 squared. And if we square the right, we get 5 plus 2, all squared. And since this was true, this must be true as well. But then there's actually something else that we can say too. We said that you only need to do to one side what you do to the other if you're changing the value. So it is possible to actually do things to the left or the right that do not change the value of this expression. So for example, if we took this expression over here, we could multiply only the left-hand side by the number 1, because we know that the number 1 does not change the value of the left. So for example, we could use 1 to be 4 and 4. So as we can see here, I've only multiplied the left by 4 and 4. If you actually try punching the left into the calculator, you'll notice that it actually gives you the exact same value as the right-hand side as well. And if you think about it, this really does make sense, because this number over here, when you multiply by 4, then divide by 4, just ends up undoing the action of the multiplication. So it's almost like you just have this original number over here. Now, the other thing you can do is you can always replace expressions for equivalent parts, and that doesn't change the value either. So for example, you could replace 5 plus 2 all squared for 5 squared plus 2 squared plus 2 times 5 times 2, because that's the binomial expansion of the power of 2. Now we started with this really simple equality up the top, but then we made it a fair bit more complicated by the time we got down here. But it is important to see that it is still equal. So for example, we can say that 7 squared is 49, 5 squared is the same thing as 25, and 2 squared is the exact same thing as 4. And then 2 times 5 times 2 is the same thing as 20. And so even after all of this, we've still maintained equality, because the right-hand side is the same thing as 25 plus 4, which is 29, plus this 20, which is the same thing as 49. So 49 is equal to this whole thing, which is also 49. Now things are actually pretty simple when you have no pronumerals in the mix. But as soon as you start adding pronumerals in, things get a little bit more complicated. There are actually 3 possible cases for equations that contain pronumerals. So we're saying that equations with pronumerals can either be always true, sometimes true, or never true. Okay, so let's give you an example of each. For example, we can say that the expression 1 plus x equals x plus 1 is always true. And if you think about it, this actually makes pretty good sense. For example, if you chose x to be the number 10, then 1 plus 10 is the same thing as 10 plus 1. Obviously it is. So that means we can say that expressions that are always true are also the same thing as equivalent expressions. Now, if you actually tried to perform algebra on an equivalent expression, it turns out that you should always be able to end up with 0 equals 0. So to demonstrate this, I've copied out our example. If we have 1 plus x equals x plus 1, we could always subtract 1 from both sides, and if this is true, then it would still be true if we subtracted 1. And then you can immediately see that these ones just cancel, and these ones over here cancel as well. So you're just left with x equals x. But one thing we can also do is we can also subtract x from both sides as well. And if this is true, it's going to stay true if we subtract x from both of the sides. So now we see that on the left, this x cancels out with this x, and this x on the right cancels with this x as well. So we're just left with 0 equals 0. So as we can see, if we start off with an equivalent expression, no matter what it is, it should always be possible to simplify it to 0 equals 0. Because 0 is equal to 0, and this is a true statement, then this one will always be true as well, no matter what the value of x is. Now some expressions, like 2x squared minus 7x equals x, are only going to be true for some specific values of x. Most values you choose will just not work. Just to show this to you, let's pick some random values. For example, if we choose x to be equal to 1, then we can immediately see that 2 times 1 squared minus 7 times 1 is not going to be the same thing as 1, because 2 times 1 squared is 2, minus 7 is minus 5. And we can very clearly see that minus 5 is not the same thing as 1. So that means this expression is false when x is equal to 1. On the other hand, if we try x equal to 4, we can see that 4 squared is 16, and then 16 times 2 is 32. And then from that, we're going to subtract 7 times 4, which is 28. Now 32 minus 28 is the same thing as 4. And in this case, we can therefore see that 4 is the same thing as 4. So this expression is true when x is equal to 4. Now, as we saw here, this expression over here is actually false when x is equal to 1, but it's true whenever x is equal to 4. We could go ahead and actually draw this on a number line here. We can see that it's false when x is 1, but it's true when x is 4. So then we come up with 2 important questions here. How often is this true? And for what values of x is this going to be true? How did I find that x equals 4? Now, learning how to actually answer these questions for a whole bunch of different expressions is going to occupy most of the rest of this topic. But then we should look at the last case here, which is a situation where the expression is never true. So this last case is the situation that can never actually be true. It's basically asking us to look for a number x, which when we add 3 to it, is equal to itself. Now, just from that, I hope you can see that it's never going to be true. No number plus 3 is equal to itself. Now, any time you get a value that's never true, you should be able to simplify it to a false statement. So let me show you this by copying it over to the right again. Now for this expression, if it's true right now, then subtracting something from both sides won't change the value. So if we go ahead and subtract x from both sides, we get the following. So we've got the expression 3 equals 0. Now since 3 does not equal 0, then this is obviously a false expression. Now because you took this expression and simplified it to a false expression, then it must be the case that your original expression was also false. So therefore we come to the conclusion that no matter what value of x you choose, this expression is always going to be false. And this just about completes all the examples I wanted to show you for this case. Now in these cases, we mostly care only about the situations where the expression is sometimes true. Because when the expression is always true or never true, those expressions are rarely interesting and they don't usually show up in applications. Now because we'd say that equivalent expressions are always true, this is the main reason why the equal sign gets used instead of the equivalent sign. So from now on, I will just use the equal sign to mean equivalence as well. It is a bit lazy, but you're going to get used to it as you see more and more examples. So now we'll also talk about the algebra of inequalities as well. So what I've written here is that algebra is harder with inequalities because the golden rule doesn't always work. Sometimes it actually completely breaks down. Now this isn't always true. It does actually work in some cases, so let me show you one first. Okay, so we know that 3 is less than 4. So for example, if we subtracted 2 from both sides, this expression would actually remain true. So in the case where we did subtract 2, we would get 1 is less than 2. And as you can see here, this is still true. So by subtracting a number like 2, if you started with a true expression, you still get a true expression, even for inequalities. However, this sort of thing doesn't always work. So for example, if I took this expression and multiplied both sides by -1, you see something else happens. So when we multiplied 3 by -1, we get -3. And when we multiplied 4 by -1, we get -4. And this expression now is actually completely false. In this case, you actually have to flip this sign to make it true, because -3 is actually bigger than -4. And this is totally clear when we actually look at it on a number line. Notice that this -4 ends up to the left when it started on the right. So that means you actually have to flip the sign anytime you multiply by a negative number. Now, in the case of multiplying by -1, the side effect is actually really straightforward. All you really need to do is to just flip the sign. But if you apply other operations, sometimes the side effects are not so obvious. So for example, if we started with the same expression, 3 less than 4, what if we took the reciprocal of both sides? What would happen? Well, on the left you'd end up with 1/3, and on the right you'd end up with 1/4. But if you think about it, it turns out that 1/3 is actually bigger than 1/4. So again, you need to flip the sign here. But this isn't always the case. You don't always flip the sign when you take the reciprocal. So for example, consider the next case. -3 is also less than 4. Well, in this case, if you took the reciprocal, the left-hand side would be -1/3, and the right-hand side would be 1/4. But this time, since -1/3 is actually a negative number, it still must be smaller than 1/4. So the idea here is that the reciprocal is not so well behaved. Simply taking the reciprocal does not necessarily mean you always have to flip the signs. Now, as you can imagine here, throwing pronumerals into these expressions is going to turn this into a huge nightmare, because we're going to have to treat the signs differently based on the value of the pronumeral. And for this reason, we really do prefer equality. So anytime we can actually convert our problem into a problem of equality, we will definitely tend to prefer that, rather than solving an inequality like one of these. But this is something I'm sure you're going to see a lot of as we continue our studies of algebra. So at this point, I'd just like to summarize everything. In this lesson, we first talked about comparison operators, like the equal sign or the less than sign. We said that an algebraic expression is just an expression that involves pronumerals and some comparison operator. Most often, it's going to be equality. For algebraic expressions that contain equalities, we call them equations, and we can solve them by using this golden rule here that says anytime you change the value of the left or the right, you must also do the same to the other side. After this, we said that equations can take one of three forms: ones that are always true, ones that are sometimes true, and ones that are never true. We then explained that the equations we're most interested in are the ones that are sometimes true, because those are the ones that are going to show up in most applications. We then looked at the algebra of inequalities and explained that it's going to be much harder because this golden rule here does not always work for them. For example, when you multiply by -1, you actually have to flip the sign. Now, where we go from here is, we want to look at these expressions that are sometimes true, and we want to try solving for all the values of x that make it true. The two main questions that we want to answer are, what values of x make it true, and how many values of x will make it true? Now we're going to actually start solving for these values of x in the next lesson, so tune into that to see exactly how it's going to be done. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.